Look up at the night sky. What do you see? Stars, galaxies, the vast emptiness stretching beyond our comprehension. But here's the unsettling truth. Everything we can observe, every glittering speck of light, accounts for less than 5% of the universe's total mass. The rest, an invisible, enigmatic force that defies detection yet holds the cosmos together. Scientists call it dark matter, and its most mysterious structures, the cosmic dark matter halos, are the hidden architects of everything we see. These colossal, ghostly shells wrap around galaxies like invisible glue, dictating their motion, their shape, even their very existence. Without them, the universe as we know it would fly apart. But here's what's truly mind-bending. We have no idea what they're made of. Galaxies move in ways that shouldn't be possible, spinning faster than the laws of physics allow, unless something unseen is pulling the strings. Picture this, a galaxy like our Milky Way, its stars orbiting the center at breakneck speeds. Logically, those stars should fling outward, torn away by centrifugal force. But they don't. Something massive and invisible holds them in place. That's the dark matter halo at work. Think of it as a cosmic puppeteer, its shadowy fingers gripping everything within its reach. And yet, despite their colossal influence, these halos remain one of the universe's greatest puzzles. They don't emit light, they don't absorb it, they don't interact with ordinary matter in any way we can directly measure. They're ghosts woven into the fabric of space itself, detectable only by the gravitational ripples they leave behind. That's where the real mystery begins. Because the more we study these halos, the stranger they become. Some stretch across millions of light years, far larger than the galaxies they surround. Others seem to defy the very laws of physics, with densities that warp our understanding of gravity. And then there are the anomalous galaxies moving in unison across unimaginable distances, as if connected by invisible threads woven into the dark matter web. What are these halos truly made of? Why do they behave in ways that challenge everything we know? Buckle up, because today we're diving deep into 25 of the most astonishing mysteries hidden within these cosmic shadows. From their bizarre structures to their role in the fate of the universe, we're about to uncover why dark matter halos might just be the greatest unsolved riddle in all of science. The first jaw-dropping mystery emerges when you compare dark matter halos to the galaxies they cradle, because these invisible giants make their cosmic hosts look tiny by comparison. Take our own Milky Way. While its shimmering spiral stretches 100,000 light-years across, its dark matter halo extends 10 times farther, engulfing everything in a sphere 1,000,000 light-years wide. Yet the most astonishing part, this colossal structure weighs 30 times more than all the stars, gas, and planets in our galaxy combined. It's like comparing a speck of dust to an invisible elephant standing right beside it, except we can't see, touch, or photograph the elephant in any way. Scientists first stumbled upon this enigma when studying galaxy rotation in the 1970s. They expected outer stars to move slower, like planets farther from the sun. Instead, stars at a galaxy's edge race just as fast as those near the center, as if invisible hands were spinning the entire structure like a solid plate. The only explanation, an immense unseen mass must surround each galaxy, its gravity gripping stars with an unshakable hold. But here's what keeps physicists awake at night. These halos don't behave like ordinary matter. They don't clump at galaxy centers like stars do. Instead, they form vast, diffuse clouds thinning gradually at the edges. This leads to another head-scratcher. If dark matter particles exist, as most theories suggest, why don't they pile up? Ordinary matter cools and condenses, collapsing into dense objects like stars. But dark matter seems immune to this process, remaining stubbornly spread out. Some theories suggest these particles simply don't interact enough to shed energy, like bumper cars that never actually collide. Others propose they're moving too fast to stay trapped, zipping through galaxies like cosmic ghosts. Yet every hypothesis hits the same wall without detecting the particles directly. We're left studying shadows cast by something we can't see. Perhaps most unsettling is how these halos sculpt the universe while leaving no fingerprints. Their gravity not only binds galaxies but warps the very fabric of space-time, bending light from distant objects in phenomena called gravitational lensing. Through these cosmic magnifying glasses, we've mapped halos so vast they distort entire galaxy clusters, yet their true nature slips through our fingers like smoke. What cosmic recipe brews structures so massive yet so elusive? The answer might rewrite physics itself. Here's something that doesn't add up. Our cosmic neighborhood is missing galaxies. Not just one or two, but hundreds. According to the most sophisticated simulations of dark matter halos, the Milky Way should be surrounded by thousands of tiny satellite galaxies, each held in orbit by its own smaller dark matter halo. Yet when astronomers count them, they find only a few dozen. This glaring mismatch, known as the missing satellite problem, has haunted scientists for decades, and it points to something fundamental we're getting wrong about how dark matter behaves. The puzzle began when supercomputer models simulated the birth of a galaxy like ours. Gravity pulls dark matter into a vast cosmic web, with dense knots forming halos of different sizes. Smaller clumps should survive, becoming the seeds for satellite galaxies like islands scattered around a mainland. But when telescopes scanned our skies, they came up shockingly short. Where simulations predicted hundreds of faint companions, reality offered barely 30. It's as if someone erased 90% of the galaxies we should be seeing. Some researchers think the answer lies in dark matter itself. The most popular theory assumes it's cold, slow-moving and clumpy, perfect for building halos of all sizes. But what if it's not? If dark matter particles were slightly warmer, zipping around faster, they'd smooth out those tiny clumps, preventing them from forming galaxies. Others suggest our telescopes just aren't sensitive enough yet. Many missing satellites could be ultra-faint. Their stars spread so thin they're nearly invisible against the blackness of space. Then there's the wild card, cosmic violence. Larger galaxies like ours might have torn apart countless smaller ones over billions of years, leaving behind only scattered starlight as evidence. Recent discoveries of ghostly stellar streams wrapping around the Milky Way support this idea. These cosmic scars hint at ancient collisions where smaller galaxies were shredded by gravity, their dark matter halos dissolving into the background like sugar in water. But the plot thickens. Even when we account for destroyed galaxies, the numbers still don't line up. Some simulations now suggest dark matter halos might exist exactly as predicted, but without the galaxies inside them. If conditions weren't right for star formation, these invisible halos could be floating around us right now, empty and undetectable. Imagine entire cosmic structures, massive enough to cradle galaxies, sitting dark and silent. Whatever the explanation, the missing satellite problem forces us to rethink everything from galaxy formation to the very nature of dark matter. Each possible solution leads to deeper questions. Are our telescopes failing us? Is dark matter more complex than we thought? Or is the universe playing by rules we haven't even discovered yet? One thing's certain: until we solve this riddle, our understanding of the cosmos remains incomplete. One of the fiercest debates in modern cosmology centers on what lies at the heart of dark matter halos specifically, whether they're packed with dense, sharp peaks or if their cores blur into smoother, flatter distributions. The controversy sounds technical, but its implications shake the foundations of physics. Computer simulations predict halos should form with cusps, steeply rising densities at their centers, like a mountain with an impossibly sharp peak. Yet when astronomers measure real galaxies, they find cores instead gentler, plateau-like central regions, more like rounded hills than jagged summits. This discrepancy between theory and observation is the cuspy core problem, and solving it may force us to rewrite the rules of dark matter itself. The roots of this conflict trace back to the 1990s, when supercomputers first modeled how dark matter halos should evolve. Every simulation spat out the same result: halos with density that spiked dramatically toward the center. Picture a teaspoon of material suddenly weighing as much as a freight train. But observations told a different story. When scientists studied the rotation speeds of stars in dwarf galaxies, small cosmic laboratories where dark matter dominates, they found motions too sluggish to match the simulated cusps. Instead of a sharp gravitational grip, the data pointed to a softer embrace. Some theorists argue this means our simulations are missing key physics. Dark matter might interact with itself in ways we haven't accounted for, perhaps through some exotic force that smooths out the cores over time. Others propose that ordinary matter, stars and gas, plays a surprising role. As galaxies form, violent supernova explosions could slosh dark matter around like water in a spinning bucket, eroding those sharp central peaks into gentler slopes. There's even a radical idea that dark matter isn't a single type of particle at all, but a mix of different species with unique behaviors that collectively sculpt halos into unexpected shapes. Then there's the observational challenge. Measuring dark matter's distribution requires pinpointing how its gravity tugs on stars and gas. But galaxies are messy places with supermassive black holes, magnetic fields, and turbulent gas clouds muddying the signal. Some apparent cores might just be illusions caused by our limited tools. A handful of recent studies claim certain galaxies do show hints of cusps after all, reigniting the debate. What makes this mystery so critical is that dark matter's inner structure acts as a fingerprint, revealing clues about its fundamental nature. Cold dark matter, the leading theory, predicts those steep cusps. If cores are real, we might need warm dark matter instead, with particles lightweight and speedy enough to avoid piling up sharply. Or perhaps dark matter isn't particulate at all, but a mysterious fluid governed by entirely new laws of physics. The stakes couldn't be higher. Get this wrong, and our entire cosmic blueprint, from galaxy formation to the universe's large-scale structure, might need revision. Future telescopes like the Vera Rubin Observatory aim to settle the debate by mapping millions of galaxies in unprecedented detail. Until then, the cuspy core controversy remains one of the most heated battles in astrophysics, where the invisible architecture of the universe hangs in the balance. Here's a paradox that cracks open our understanding of dark matter halos. Some of them are just too big to fail. According to our most advanced simulations, certain halos are so massive, their gravity should have easily pulled in enough gas and stars to form bright, bustling galaxies. Yet when we look, we find nothing but darkness. These cosmic voids shouldn't exist, yet they're scattered across the universe like ghost towns where metropolises ought to be. Scientists call this the too big to fail problem, and it's forcing us to question whether dark matter halos play by rules we've yet to uncover. The mystery came into focus when researchers compared simulated universes to real observational data. Supercomputers predicted hundreds of hefty dark matter halos lurking around large galaxies like ours, halos so gravitationally powerful they should have birthed satellite galaxies as bright as the small Magellanic Cloud. But reality delivered a shock. Instead of thriving galactic neighbors, astronomers found these halos either hosted puny, dim galaxies or, more baffling, nothing at all. It's as if the universe handed these structures every ingredient for success, yet they somehow skipped star formation entirely. One leading theory suggests that cosmic reionization, a period when the early universe flooded with harsh ultraviolet light, might have sterilized these halos. As the first stars and galaxies ignited, their intense radiation could have heated surrounding gas, making it too energetic to collapse into new stars. Smaller halos, lacking the gravity to hold onto their gas, would have been stripped bare, leaving them permanently dark. But here's the catch. The too big to fail halos are massive enough to resist this stripping. They should have clung to their gas and formed galaxies anyway. So why didn't they? Another possibility is that dark matter interacts differently than we've assumed. If dark matter particles have even a tiny ability to bounce off one another or interact through some unknown force, it could redistribute energy within these halos, puffing them up and weakening their gravitational grip. This would make it harder for gas to condense into stars, leaving the halos eerily empty. Some simulations now include this self-interacting dark matter, and intriguingly, the results begin to match observations better. Or perhaps the answer lies in the chaotic history of galaxy formation. Larger halos might have experienced violent mergers or bursts of star formation that drained their gas reserves early on, leaving them barren. Imagine a dark matter halo as a cosmic construction site that ran out of bricks before the builders could finish. Without enough gas to fuel new stars, these halos would remain shadowy shells of their potential. What makes this enigma so urgent is that it strikes at the heart of galaxy formation itself. If our best simulations can't predict why some halos stay dark, how much else are we missing about how galaxies are born? Future telescopes like the James Webb Space Telescope are now peering into these voids, hunting for faint traces of stars or gas that might crack the case. Until then, the too big to fail problem stands as a glaring reminder that dark matter halos might be hiding secrets that rewrite the cosmic rulebook. Stretching across the night sky like celestial brushstrokes, ghostly ribbons of stars drift far beyond their parent galaxies, remnants of ancient star clusters torn apart by gravity's relentless pull. These are tidal streams, and they're more than just cosmic debris. They're the universe's way of sketching the invisible hand of dark matter halos in starlight. When a globular cluster or dwarf galaxy ventures too close to a larger galaxy's halo, gravitational tides stretch it into a filamentary river of stars, sometimes spanning hundreds of thousands of light years. These phantom trails should, in theory, trace the halo's gravitational field like ink dispersing in water. But what astronomers are finding defies expectations, revealing a dark matter landscape far stranger than simulations predicted. Take the case of the Milky Way's most famous tidal stream, the Sagittarius Stream. This glittering arc, the shredded remains of a dwarf galaxy consumed by our own, wraps around the galaxy in a looping orbit. By tracking its star's motions, astronomers hope to map the dark matter halo's shape, assuming it would be smooth and symmetric, like a vast invisible sphere. Instead, the stream kinks and splinters in ways that suggest our halo is lumpy, asymmetrical, or even spinning. It's as if we're seeing the wake of a ship, but the ocean's currents make no sense. Some segments of the stream move faster, others slower, as if dark matter isn't uniformly distributed but clumped in unseen pockets. Even more puzzling are streams that shouldn't exist at all. In 2019, astronomers discovered the Phoenix Stream, a stellar ribbon so pristine, its stars orbit in near-perfect synchrony, as if the cluster that birthed it was disrupted only recently. Yet simulations show such coherence should be impossible after billions of years orbiting through a turbulent dark matter halo. It's like finding a glass bottle intact after being tumbled in a stormy sea. Some researchers now suspect dark matter halos might have substructure, smaller, denser clumps within them that act like hidden rocks in a river, diverting tidal streams in unpredictable ways. Then there's the bizarre case of parallel streams. In 2021, the Gaia spacecraft revealed two stellar streams named Nix and Levens, orbiting the Milky Way in nearly identical paths but separated by tens of thousands of light years. How could two independent structures end up moving in such perfect harmony? One tantalizing explanation involves dark matter's gravitational wake. As massive objects move through the halo, they might generate ripples in the dark matter density, creating invisible channels that guide subsequent streams like rails. If true, it would mean tidal streams aren't just passive tracers of dark matter, they're actively interacting with it, a dynamic dance between the seen and unseen. The ultimate irony, these stellar ghosts born from destruction are becoming our best tools for studying the indestructible. By analyzing how tidal streams twist, break, or accelerate, astronomers are reverse engineering the halo's hidden architecture. Already, discrepancies between observed streams and simulations hint that dark matter might be colder or warmer than we thought, or that halos are far more textured than the smooth profiles theory assumes. Every kink in a stream, every anomalous gap, whispers secrets about the invisible scaffolding holding our universe together. And with new telescopes like the Vera Rubin Observatory set to discover thousands more streams in the coming decade, we're on the verge of decoding dark matter's gravitational language, one stellar trail at a time. Spiral galaxies like the Milky Way shouldn't exist, at least not according to gravity alone. Picture a spinning vinyl record. The outer edge moves faster than the center, fighting centrifugal force to stay intact. Now imagine that record is a galaxy, its stars whirling at breakneck speeds. Without some unseen anchor, those outer stars should fling into the void, tearing the galaxy apart. Yet spiral after spiral defies this fate, their elegant arms holding together with impossible grace. The secret dark matter halos aren't just passive observers, they're master sculptors, shaping galaxies into the iconic forms we recognize across the cosmos. Here's where it gets fascinating. While dark matter halos envelop galaxies in vast spherical clouds, the luminous disks of spiral galaxies, the parts we actually see, are razor-thin by comparison. How does a diffuse, formless halo give rise to such precision? The answer lies in an intricate cosmic dance between dark and ordinary matter. As gas and dust first fell into the gravitational wells of primordial halos, they carried something dark matter couldn't: friction. Colliding and swirling, this ordinary matter shed energy, collapsing into a spinning disk while the dark matter remained aloof, maintaining its sprawling, spherical shape. The halo's gravity provided the scaffolding, ordinary matter did the rest, but some galaxies throw a wrench in this elegant theory. Take ultra-diffuse galaxies, ghostly, sprawling spirals so faint they're nearly transparent. These cosmic anomalies contain as much dark matter as the Milky Way, yet their stars are scattered so thinly, their halos seem to have failed at concentrating ordinary matter effectively. Even stranger are dark disk galaxies, where observations suggest some dark matter may have settled into the galactic plane, mimicking the behavior of stars. If confirmed, this would upend the assumption that dark matter only interacts gravitationally, hinting at undiscovered forces at play. Then there's the Milky Way's own dark matter halo, which recent studies suggest might be slightly flattened, not perfectly spherical. This subtle squashing could mean our halo carries a memory of the galaxy's turbulent past, perhaps a long-ago collision or an asymmetry in how ordinary matter funneled into it. Even more provocative are galaxies like Dragonfly 44, which emits almost no light yet weighs as much as the Milky Way. Its dark matter halo didn't just influence galaxy formation, it completely dominated it, leaving almost no trace of stars behind. The deeper we look, the clearer it becomes. Dark matter halos and galaxies aren't just connected, they're locked in a feedback loop. Halos dictate where galaxies form, but galaxies, in turn, might reshape their halos through billions of years of mergers, bursts of star formation, and the gravitational wakes of orbiting satellites. Some theorists now argue that the halo's inner regions could even learn from their galaxies, their densities adjusting to match the baryonic matter they host. It's a cosmic conversation we're only beginning to decode, one that might reveal why the universe favors spirals, how disks stabilize over eons, and what truly binds a galaxy together. Every spiral we observe is a testament to dark matter's invisible hand, a delicate balance between chaos and order written in the language of gravity. But with each anomaly, each galaxy that breaks the mold, we're reminded that the rules of this dance are far from settled. Perhaps the most profound lesson is this: to understand the galaxies we see, we must first unravel the mysteries of the halos we don't. Imagine a galaxy where the stars are spread so thin, you could fly a spaceship through it for thousands of light years and barely glimpse a handful of suns. These aren't science fiction, they're ultra-diffuse galaxies, some of the most baffling cosmic specters ever discovered. So faint that many were only spotted in the last decade thanks to hypersensitive telescopes. These ghostly islands defy everything we thought we knew about how galaxies form. Here's the twist: despite having almost no visible matter, many of them weigh as much as the Milky Way, their mass lurking almost entirely in the form of dark matter halos that shouldn't behave this way. Take Dragonfly 44, a galaxy in the Coma cluster that emits just 1% of the Milky Way's light, yet contains a staggering dark matter halo. At first glance, it looks like a cosmic accident, a galaxy that forgot to form stars. But the real shock came when astronomers measured its halo's mass. Instead of the expected wispy structure, they found a gravitational grip so strong it rivaled our own galaxies. This makes no sense under standard models, where visible matter and dark matter grow in tandem. It's like finding a hollowed-out skyscraper that somehow still weighs as much as a solid one. The puzzle deepens when you study how these galaxies survive. Most ultra-diffuse galaxies exist in violent environments, dense galaxy clusters where gravitational tides should shred fragile structures. Yet they persist, their stars inexplicably clinging together against all odds. Simulations suggest their halos must be unusually puffy, with dark matter spread out in a way that cushions against disruption. But why? One theory points to ancient supernova. In these galaxies' early days, intense star formation might have blasted away gas, leaving behind a skeletal structure held together by an overgrown dark matter halo. Others propose these galaxies are failed giants' halos that somehow missed their chance to collect enough gas to form stars, leaving them dark and diffuse. Then there's the bizarre case of NGC 1052DF2, an ultra-diffuse galaxy that appears to have almost no dark matter at all. This discovery sent shockwaves through astronomy, because if dark matter halos are the universe's invisible scaffolding, how could an entire galaxy build itself without them? Some argue this outlier might have had its dark matter ripped away by a violent collision, while others wonder if we're seeing a wholly new class of galaxy, one that forms under rules we haven't written yet. What makes this enigma so thrilling is that ultra-diffuse galaxies aren't rare oddities. They might outnumber galaxies like ours. Their existence forces us to reconsider dark matter's role in galaxy formation. Perhaps halos are more dynamic than we thought, their shapes and densities changing based on the chaotic histories of the galaxies they host. Or maybe star formation isn't just about gravity, but about delicate balances between gas, radiation, and dark matter that we've only begun to glimpse. One thing's certain: in the ghostly light of these cosmic whispers, the rules of the universe are being rewritten. Galaxies spin, some lazily, others at dizzying speeds, but here's what nobody saw coming: the dark matter halos surrounding them barely rotate at all. This is the spin paradox, and it's throwing a wrench into our understanding of cosmic evolution. According to simulations, when dark matter halos form from collapsing gas in the early universe, they should have spun up like figure skaters pulling their arms in, reaching noticeable rotational speeds. Yet when astronomers measure them, most halos show almost no rotation, less than 5% the speed of their host galaxies. It's as if the universe's largest structures are stuck in slow motion while everything inside them whirls in fast forward. The discovery came as a shock because rotation isn't just a side effect of structure formation, it's fundamental. As primordial gas fell into dark matter halos, it carried angular momentum, the same force that makes a pizza dough spin when tossed. That spin should have transferred to the dark matter itself, setting the entire halo into motion. Instead, measurements reveal halos acting like cosmic deadweights, their sluggish rotation barely influencing the galaxies they cradle. Some halos even spin backwards relative to their galaxies, like a carousel rotating counter to the horses atop it. One theory suggests dark matter's infamous aloofness might be to blame. Unlike ordinary matter, dark particles don't collide or generate friction. Without these interactions, angular momentum simply can't distribute efficiently through the halo, leaving most of it non-rotating while gas and stars condense into spinning disks. Others propose that mergers, violent collisions between halos over billions of years, might have scrambled their rotation, cancelling out spins like opposite spinning tops colliding. Simulations show that when halos merge, their rotational energies don't add up neatly. Instead, they often leave behind a halo that's nearly stationary. But there's a catch. A handful of halos do exhibit strong rotation, and these outliers are even more perplexing. Take the galaxy NGC 2664, whose halo spins at nearly a third the speed of its disk, far faster than most. If dark matter can rotate this briskly in some cases, why not others? The answer might lie in a cosmic game of chance. Halos born from exceptionally smooth patches of the early universe, where gas flowed in uniformly, could have retained more spin, while turbulent regions produced halos with cancelled rotations. The stakes of this paradox are enormous. Rotation shapes galaxies without it, disks wouldn't flatten, spiral arms wouldn't wind, and bars wouldn't form. If halos barely spin, their gravitational influence on these structures becomes far more passive than we assumed. Some cosmologists now wonder if we've overestimated dark matter's role in sculpting galaxy shapes, or if hidden interactions between dark and ordinary matter are subtly tweaking rotational dynamics. What's clear is that the spin paradox exposes a gap in our cosmic blueprint. Whether the solution lies in dark matter's particle properties, the chaos of halo mergers, or some undiscovered torque in the early universe, one thing's certain: the stillness of these halos is spinning our theories into uncharted territory. Simulations of our universe paint a crowded cosmic picture, dark matter halos nested within larger halos like Russian dolls stretching down to scales smaller than planets. According to theory, the Milky Way's vast halo should be teeming with thousands of these subhalos, miniature versions of itself, each weighing anywhere from 1,000,000 times the mass of the Sun down to mere asteroids. But when astronomers scan the skies, they find only a fraction of the expected population. This isn't just a case of overlooked objects, it's a glaring mismatch between prediction and observation that could rewrite our understanding of dark matter's smallest scales. The roots of this mystery dig deep into how structure forms in the universe. Dark matter's gravitational pull creates a cosmic hierarchy, with enormous halos hosting smaller ones, which in turn host even smaller clumps. Sophisticated simulations like Via Lactea and Aquarius show this cascade continuing almost indefinitely, predicting subhalos so numerous they'd outnumber visible stars. Yet when researchers tally the Milky Way's satellite galaxies, the most obvious tracers of these subhalos, they count fewer than 60 where thousands should exist. It's as if someone snipped an entire branch off dark matter's family tree. One possible explanation lies in the nature of dark matter itself. If it's warmer than the standard cold dark matter model assumes, meaning its particles move faster, they'd smooth out the smallest density fluctuations, preventing the tiniest subhalos from forming. Imagine trying to build a sandcastle with grains too fine to hold their shape. Alternatively, if dark matter interacts with itself through some unknown force, collisions between particles could puff up subhalos, making them too diffuse to host detectable galaxies. Then there's the observational hurdle. Subhalos without stars are effectively invisible, detectable only through their gravitational effects. Some might reveal themselves by bending light from distant quasars in fleeting microlensing events, but these are needle-in-haystack observations. Others could betray their presence by disturbing thin stellar streams, those ribbons of stars torn from passing clusters. Recent studies of the Milky Way's orphan stream show unexplained kinks that hint at close encounters with unseen subhalos, like ripples from a pebble dropped in a pond we can't see. Perhaps the most tantalizing clue comes from gamma rays. Some subhalos might occasionally annihilate their own dark matter particles, producing faint bursts of high-energy light. Fermi telescope data has flagged dozens of unexplained gamma-ray sources that align with nowhere we've mapped. Could these be the glowing graves of dark matter clumps? The implications stretch far beyond our galaxy. If subhalos are truly missing, it might mean dark matter isn't the simple, sluggish particle we've assumed. Or perhaps the universe has a minimum size for cosmic structures, a fundamental cutoff below which gravity can't assemble dark matter into bound clumps. Either scenario would force us to redraw the blueprints of cosmic evolution. With next-generation telescopes set to probe fainter and smaller scales than ever, we're on the verge of answering a profound question. Are we failing to see the subhalos, or did they never exist at all? Gravity doesn't play favorites, it pulls equally in all directions, so logic says dark matter halos should be perfect spheres. Right, wrong. When astronomers finally mapped their true shapes, they found halos twisted into flattened ovals, triaxial ellipsoids, even lopsided distortions that look like cosmic fingerprints. This isn't just a quirk, it's a full-blown rebellion against the standard model of cosmology, where halos were supposed to form as near-spherical blobs. Instead, we're staring at a universe where dark matter structures have more in common with squashed footballs than marbles. The first clues emerged from galaxy rotation curves. If halos were perfectly round, stars orbiting at different angles would move with predictable symmetry. But telescopes caught stars speeding up or slowing down depending on their orbital path, like cars on a racetrack with hidden dips and rises. The only explanation, the underlying dark matter must be distributed asymmetrically, its gravity warping space unevenly. Even our own Milky Way's halo shows hints of flattening, as if some invisible hand pressed down on its poles. Then came the slam-dunk evidence, gravitational lensing. When dark matter halos bend light from distant galaxies, the distortions reveal their true silhouettes. Some, like the halo around galaxy cluster El Gordo, stretch into elongated arcs resembling cosmic taffy pulled by unseen forces. Others, like those in the Able 1689 cluster, twist into triaxial shapes, three-dimensional ellipsoids where each axis has a different length. It's as if the universe rolled dark matter into abstract sculptures, defying every expectation of symmetry. Why the cosmic rebellion? One leading theory points to spin. While dark matter halos overall rotate sluggishly, their inner regions might carry just enough angular momentum to bulge at the equator, like a planet spinning itself into an oblate shape. Others argue that mergers, violent collisions between halos over billions of years, leave behind scars, stretching structures into irregular forms. Picture two globs of dough smashing together. They wouldn't reform a perfect sphere, but some messy, flattened hybrid. But here's the twist, some halos seem to remember their history. Simulations show that halos forming in quieter cosmic neighborhoods with smoother gas inflow tend to stay more spherical. Those born in chaotic regions, fed by turbulent streams of matter, grow increasingly distorted. This suggests a halo's shape might encode its entire life story, a fossil record written in invisible matter. The real shocker, these odd shapes might solve other mysteries. Flattened halos could explain why some galactic disks warp at their edges, or why certain stellar streams follow bizarre, non-circular orbits. If dark matter isn't evenly distributed, its gravitational kicks could nudge stars and gas in unpredictable ways. Suddenly, anomalies astronomers once dismissed as noise could be vital clues to the halo's true architecture. Yet for all we've uncovered, the biggest question remains unanswered. What fundamental physics dictates these shapes? Is dark matter subtly interacting with itself, creating internal pressures that mold halos like clay, or does ordinary matter, stars and gas, somehow drag dark matter into alignment like wind shaping a dune? Every oddball halo we find chips away at the idea that dark matter is simple and inert. Instead, it's beginning to look like an active participant in cosmic evolution, its forms as varied and dynamic as the galaxies it hosts. One thing's certain: the universe has no love for perfect symmetry. In the hidden realm of dark matter, imperfection isn't just common, it's the rule. And each distorted halo whispers the same tantalizing secret: we're missing something fundamental about the invisible 85% of the universe's matter. Whatever it is, it's bending the rules right before our eyes. We just have to learn how to see it. Take everything you know about temperature in space and throw it out the window because dark matter halos are breaking the rules. We've long assumed these invisible structures would be cold, uniform places, their particles drifting lazily under gravity's gentle pull. But new observations reveal something startling. Pockets of dark matter halos seem to be heating up and cooling down in ways that defy explanation. It's as if we've stumbled upon invisible celestial furnaces flickering to life in the void. This isn't just a curiosity, it could be the first clue that dark matter interacts with forces beyond gravity, something physics never saw coming. The first hints of this anomaly came from galaxy clusters, where hot gas fills the spaces between galaxies like a cosmic atmosphere. By mapping the gas temperatures, astronomers noticed something off: the heat wasn't distributed evenly. Some regions were inexplicably hotter or colder than the surrounding dark matter halo should allow. The oddest part: these temperature variations didn't align with any visible sources of energy like black holes or starbursts. Something invisible was stirring the pot. One radical explanation suggests dark matter particles might occasionally collide, releasing energy like microscopic fireworks. In most models, dark matter is collisionless. It passes through itself like ghosts through walls. But if particles do interact, even weakly, those rare encounters could generate heat, creating warm spots in the halo. Picture a crowded dance floor where most dancers never touch, but every few hours, two accidentally bump and send a ripple through the room. Then there's the eerie case of cold flows. In some halos, filaments of chilly gas snake through the hot medium like icy rivers, a phenomenon that shouldn't persist without dark matter somehow shielding them from the surrounding heat. Some theorists propose these cold streams might trace hidden magnetic fields woven through the halo, with dark matter acting as an invisible conductor. It's a wild idea: dark matter not just responding to gravity, but somehow entangled with electromagnetism's unseen forces. The most tantalizing data comes from halos around ancient quasars. These cosmic lighthouses, powered by supermassive black holes, blast their surroundings with radiation, yet their dark matter halos show temperature patterns that mirror the quasar's activity, as if the halo is remembering past energy injections. This implies a feedback loop we can't yet explain: ordinary matter influencing dark matter, not just the other way around. What makes this mystery so urgent is the sheer scale of implications. If dark matter exchanges energy even occasionally, it would mean our universe's missing mass isn't just a passive backdrop, but an active participant in cosmic evolution. Heat could determine how halos clump, how galaxies merge, even how the cosmic web itself evolves. Every anomalous temperature reading is a whisper from the dark side, one we're only now learning to hear. Think of the universe as a vast construction site, with dark matter halos as its growing skyscrapers. Some should be finished by now, others midway through, but the blueprints we're working with don't match the skyline. Astronomers have stumbled upon a baffling inconsistency. While many halos expanded predictably over billions of years, others stalled early, as if cosmic time forgot to touch them. These stagnant halos, frozen in their adolescence, shouldn't exist under our current models of cosmic evolution, yet they're scattered across the universe like abandoned buildings in an otherwise thriving city. The mystery first surfaced when researchers compared halos in dense galaxy clusters to those in the cosmic void. Logic suggests that clusters, with their immense gravitational pull, should host the fastest-growing halos, continually devouring nearby matter. Yet observations revealed the opposite. Some of the most massive halos in crowded environments stopped growing billions of years ago. Their growth stunted despite swimming in a sea of available dark matter. Meanwhile, isolated halos in emptier regions often balloon to unexpected sizes, feasting on scant resources like desert plants thriving against the odds. One theory points to a phenomenon called strangulation. In crowded galactic neighborhoods, halos might exhaust their fuel supply too soon. As galaxies cluster together, the intergalactic gas, thought to feed halo growth, gets heated to extreme temperatures, becoming too energetic to collapse into new structures. Without this fresh material, halos essentially starve, stuck at a fixed mass while the universe marches on. But this doesn't explain why some halos in similar environments continue growing, as if they've found a secret pantry of dark matter. Then there's the wild card of mergers. When halos collide, simulations show they should combine into larger structures, like droplets of water fusing. Yet some mergers appear to shatter growth instead, leaving halos permanently stunted. Recent studies of the Bullet Cluster, a famous cosmic collision, reveal that its halos didn't fully merge but instead passed through each other like ghosts, their growth rates altered unpredictably. It's as if dark matter carries a memory of these violent encounters, adjusting its behavior in ways we can't yet model. Perhaps the most startling clue comes from the ancient universe. Telescopes like the James Webb have spotted fully formed halos in regions so young they shouldn't have had time to accumulate such mass. These cosmic overachievers hint at an era of hyper-efficient dark matter assembly, a brief window when halos grew at breakneck speeds before the rules changed. Was there an early universe golden age of halo growth that shut down abruptly? And if so, why? The implications ripple across cosmology. If halos don't evolve uniformly, our entire timeline of galaxy formation might be off. Dating the universe by halo growth, once thought as reliable as counting tree rings, now looks fraught with hidden variables. Some researchers even speculate that dark matter's properties could evolve over time, its ability to clump changing as the universe expands. Others wonder if we're seeing the fingerprints of dark energy, cosmic acceleration subtly tweaking halo growth rates in ways we've yet to decipher. What's clear is this: the growth of dark matter halos isn't just a passive backdrop to cosmic history, it's an active, messy process full of surprises. And until we understand why some halos thrive while others stagnate, we're missing a critical chapter in the story of how our universe built itself. At the heart of every massive galaxy lurks a supermassive black hole, an insatiable beast with gravity so strong not even light escapes its grasp. But here's the twist: these cosmic monsters might be pulling strings far beyond their event horizons, reshaping the very dark matter halos that birthed them. This isn't a one-way street. It's a violent feedback loop where star formation, black hole eruptions, and dark matter engage in a gravitational tug-of-war that sculpts galaxies over billions of years. Consider the aftermath of a star's death. When massive stars explode as supernova, they unleash shockwaves powerful enough to blast gas out of a galaxy, and with it, the gravitational glue holding dark matter in place. These outbursts can literally push the halo's inner regions outward, like a cosmic game of tug-of-war where ordinary matter suddenly yanks the rope. Simulations show that over time, repeated stellar explosions can puff up a halo's core, transforming what should have been a steep density peak into a gentle plateau. It's dark matter's version of a facial exfoliated by starlight. But black holes take this chaos to another level. When supermassive black holes feast on gas, they don't just swallow quietly. They belch out jets of energy so intense they can heat surrounding dark matter to millions of degrees. The halo responds like a living thing, expanding where it's heated, contracting where it cools. In galaxy cluster HLAFT32, astronomers witnessed this drama firsthand. X-ray observations revealed cavities in the hot gas carved by black hole jets, and the dark matter distribution followed these scars like a shadow. The weirdest part, this feedback might work both ways. Just as black holes alter their halos, the halos could be feeding the beasts. Some theories suggest dark matter particles occasionally collide at the galaxy's center, annihilating into gamma rays that provide just enough energy to keep the black hole active. It's a cosmic symbiosis, one that could explain why galaxies with the most massive halos often host the hungriest black holes. Yet this dance has consequences. In galaxies where feedback runs rampant, star formation can shut down entirely. Without fresh gas to birth new stars, galaxies become red and dead relics, their halos left in stagnant equilibrium. Meanwhile, in quieter corners of the universe, halos untouched by violent feedback grow denser and more concentrated, their galaxies blazing with youthful starlight. This dichotomy raises a profound question. Are dark matter halos the architects of galaxy fate, or merely the canvas upon which black holes and stars paint their masterpieces? The answer might lie in the ultimate cosmic balancing act. Too much feedback and halos expand, starving their galaxies. Too little, and halos collapse into overgrown monsters, their black holes running wild. Somewhere in between, a perfect equilibrium allows spiral galaxies like ours to thrive. It's a reminder that dark matter isn't just a static scaffold. It's an active participant in the universe's greatest power struggles, reacting and adapting to forces we're only beginning to comprehend. Every jet from a black hole, every supernova's blast, leaves an imprint on the invisible architecture of the cosmos. And if we learn to read those imprints, we might finally understand why some galaxies live fast and die young, while others burn slow and steady across the eons. Picture the gravitational field of a planet like Earth as a smooth, invisible blanket warping the fabric of space-time. Now tear that blanket into strands, not random threads, but precise, bristling filaments radiating outward like a cosmic brush. This is the bizarre premise of the dark matter hair hypothesis, where halos might not be featureless clouds, but sprout ultra-fine streams of invisible matter stretching millions of light years into the void. It's a concept so strange, even the scientist who proposed it called it hairy as a joke, but the math suggests these structures could be very real. The theory stems from a quirk of gravitational physics. When dark matter flows past massive objects like planets or stars, simulations show it shouldn't just bend subtly, it could bunch into dense, linear filaments. Think of water flowing around a rock in a stream. Some gets caught in tiny whirlpools behind it. On a cosmic scale, these whirlpools would freeze into place as permanent hairs, each strand a hyper-concentrated line of dark matter particles. The most mind-bending detail, these hairs could reach absurd lengths. A single hair sprouting from Earth, for example, might stretch halfway to the Alpha Centauri system, all while being no thicker than an atom. Detecting something so ethereal seems impossible, but the hypothesis offers a tantalizing clue. Where hairs pierce through a planet, they'd create minuscule spikes in gravity. Not enough to notice with regular scales, we're talking changes of less than a quadrillionth of Earth's gravity, but just maybe measurable with future quantum sensors. Some researchers have even proposed hunting for these hairs using GPS satellites. They're ultra-precise clocks sensitive enough to tick slightly faster or slower if a hair's gravitational whisper passes through. Yet the real fireworks start when you scale this up to galaxies. If dark matter halos have hair-like structures en masse, they could form an invisible network of gravitational tripwires crisscrossing the cosmos. Stars or gas clouds drifting through these regions might suddenly accelerate, like marbles rolling over hidden speed bumps. There's circumstantial evidence too. Certain galactic streams exhibit odd kinks that resemble objects plucking their way through a cosmic harp. Skeptics argue these hairs would be too fragile to survive the universe's chaos, shredded by galaxy collisions or smoothed out by dark matter's own diffuse nature. But supporters counter that new physics, like dark matter particles with tiny self-interactions, might act as cosmic hair gel, keeping filaments intact for billions of years. If true, halos wouldn't just be amorphous blobs, but intricate structures with topography as complex as a mountain range. What makes this idea so electrifying is its sheer audacity. Dark matter was already mysterious enough. Now we're suggesting it's styled into invisible braids and ponytails. Yet that's the thrill of frontier science. Sometimes the universe's wildest secrets hide in plain sight, waiting for us to rethink what we've overlooked. And if these hairs exist, they'd be more than cosmic curiosities. They'd be highways of invisible matter, charting paths through the darkness we've never dreamed of following. Gravity may be the universe's architect, but there's something eerie about how dark matter halos arrange themselves like cosmic neighbors conspiring in secret. Across vast stretches of the universe, astronomers have caught halos aligning their orientations in ways that defy randomness, as if some unseen hand nudged them into formation. This isn't just a quirk, it's a fundamental challenge to our understanding of how cosmic structures grow, hinting at forces or influences we've yet to map. Take the Great Wall of Galaxies, a sprawling filament of superclusters stretching hundreds of millions of light years. Within this structure, dark matter halos aren't scattered like haphazard marbles, they're angled like dominoes frozen mid-fall, their axes pointing eerily toward the filament's spine. Statistically, the odds of this happening by chance are less than 1 in 10,000. It's as if the halos remember the direction they were born, their alignments locked in place since the universe's infancy. Then there's the peculiar case of neighboring galaxy clusters. Halos separated by staggering distances sometimes spin in sync, their rotational axes parallel like gears in a machine too vast to comprehend. The most famous example, the Coma and Leo clusters, separated by over 300 million light-years, yet their dark matter halos tilt at nearly identical angles. If gravity alone shaped these structures, such coordination would be impossible, like two tops spinning in unison on opposite sides of a stadium without any connection. One radical explanation digs back to the Big Bang. Quantum fluctuations in the early universe might have imprinted primordial spin directions on dark matter, a cosmic fingerprint preserved over billions of years. Picture a crowd of dancers all starting with the same choreography. Even as they spread apart, their movements stay linked by that initial script. Another theory suggests dark matter interacts through an undiscovered long-range force, weaving halos into alignment like iron filings pulled by a magnet we can't see. But skeptics point to cosmic flows, rivers of galaxies drifting toward common gravitational attractors like the Shapley supercluster. Perhaps halos align simply because they're all swimming downstream in the same current. Yet even this falls short of explaining the precision of the matches. Flows can steer motion, but they shouldn't dictate rotation with such eerie consistency. The most unsettling possibility, this alignment might be a shadow of something deeper, an undiscovered layer of cosmic structure. Just as magnetic fields guide charged particles, some theorists propose dark fields could orient halos along invisible lines of force. If true, we're not just missing matter, we're missing an entire hidden framework sculpting the universe from behind the scenes. Every aligned halo is a breadcrumb trail leading to a truth we've yet to grasp. Whether it's a whisper from the infant universe or evidence of dark matter's secret complexity, one thing's clear: the cosmos isn't just lumpy, it's orchestrated. And the conductor's baton remains just beyond our sight. The farther back we peer into cosmic history, the stranger dark matter halos become, not just younger but fundamentally different. These ancient structures, forged when the universe was a fraction of its current age, might be hiding the ultimate cheat code to decoding dark matter's secrets. Unlike their modern counterparts, primordial halos existed in a hotter, denser cosmos, where the rules of structure formation were written in a language we're only beginning to decipher. Preserved in their ghostly architecture could be clues to dark matter's identity, frozen in time like insects trapped in amber. Consider the halo surrounding galaxy JADSGS 2835, one of the earliest known galaxies spotted by the James Webb Space Telescope. Born just 300 million years after the Big Bang, its dark matter cocoon shouldn't have had time to grow so massive under standard models. Yet there it is, a cosmic toddler wearing a gravitational suit 10 sizes too big. This anomaly suggests dark matter in the early universe clumped together faster than physics currently explains, as if the particles had properties we've yet to account for. Some theorists speculate that young dark matter might have been stickier, interacting in ways that shut off as the cosmos expanded and cooled. Others propose these ancient halos could harbor exotic states of dark matter, like Bose-Einstein condensates that formed when temperatures were extreme enough to trigger quantum phase transitions. The smoking gun might lie in their shapes. While modern halos tend toward asymmetry, the earliest ones appear eerily spherical, too perfect for the turbulent youth of the universe. Simulations of cold dark matter predict these halos should be lumpy, riddled with substructure from frequent mergers. Instead, observations hint at smooth, rounded profiles, as if some primordial force ironed out the wrinkles. One controversial idea suggests that dark photons, hypothetical particles mediating forces between dark matter, might have created a kind of cosmic pressure, smoothing halos into uniformity. If proven, it would mean dark matter isn't just a passive spectator but engages in a rich, hidden physics all its own. Then there's the puzzle of missing feedback. Today, supernova and black holes constantly reshape halos, puffing them up or carving cavities. But in the early universe, before stars died in great numbers, halos grew undisturbed, their pristine structures reflecting dark matter's unaltered behavior. Studying them is like comparing a wild, uncut diamond to one faceted by a jeweler. The original form reveals properties that later processes obscure, the most tantalizing possibility. These time capsule halos might still be with us. Ultra-faint dwarf galaxies, like those orbiting the Milky Way, are thought to be fossils from the cosmic dawn, their halos unchanged for billions of years. Their dark matter distributions, measured through stellar motions, show bizarre consistencies with theoretical predictions for ancient halos: densities too low, shapes too round, spins too slow. It's as if we've found living relics of the universe's first dark matter structures, hiding in plain sight. Unlocking their secrets won't be easy. The same qualities that make ancient halos valuable, their distance, faintness, and simplicity, also make them fiendishly hard to study. But with next-generation telescopes like the Roman Space Telescope set to map the sky in unprecedented detail, we're on the verge of opening a window into dark matter's raw, unfiltered past. What we find might not just solve the halo riddles we've encountered so far, it could rewrite the story of how the universe built itself from the darkness up. Some galaxy clusters act like cosmic illusions, gigantic gatherings of hundreds of galaxies that somehow hold themselves together against all logic, bound by gravity that shouldn't exist. These sprawling metropolises of stars appear to lack the very thing that keeps clusters intact: massive dark matter halos. It's as if the universe forgot to include the glue holding these structures together, forcing astronomers to question whether we've fundamentally misunderstood how dark matter operates on the largest scales. The mystery first emerged when scientists studied the Bullet Cluster, a pair of colliding galaxy clusters that should have been a textbook case for dark matter's role. As the clusters passed through each other, their gas clouds slowed due to friction, while their dark matter halos, unaffected by such interactions, raced ahead. The result, two distinct gravitational lenses bending light where the visible matter wasn't proof that dark matter existed. But when researchers turned their telescopes to other clusters, like Abell 521, they found the opposite problem: enormous gatherings of galaxies with gravity too weak to explain their cohesion, as if their dark matter halos had gone missing. One possible explanation lies in something called modified Newtonian dynamics, or a controversial theory suggesting gravity behaves differently at cosmic scales than our equations predict. Proponents argue clusters like these don't need dark matter because the rules of gravity change in low acceleration environments. Imagine playing a game where the ball suddenly curves midair without wind or spin. It would mean the rules of physics themselves are incomplete. Yetman struggles to explain phenomena like the bullet cluster, leaving scientists torn between rewriting gravity or accepting that dark matter behaves in ways we haven't anticipated. Another possibility is that these clusters are the cosmic equivalent of optical illusions. Perhaps their dark matter halos are so diffuse, so spread out, that their gravitational signal gets lost in the noise. Think of trying to hear a whisper in a thunderstorm. The sound exists, but the chaos drowns it out. Some simulations suggest that in extremely massive clusters, dark matter might distribute itself into a near-uniform fog. Its gravity so evenly distributed it becomes nearly invisible to conventional detection methods. Then there's the wild card merger history. Galaxy clusters grow by cannibalizing smaller groups, and if those predecessors had unusually weak halos, their combined remnants might never accumulate enough dark matter to match expectations. It's like building a sandcastle with dry sand. No matter how much you pile up, it never quite holds its shape. Recent studies of the Coma cluster reveal patches where galaxies move in lockstep without the expected dark matter scaffolding, hinting that some clusters might be stitched together more by momentum than by gravity. What makes this enigma so critical is that galaxy clusters are the universe's largest gravitationally bound structures. If our models can't explain them, we might be missing a fundamental piece of cosmic architecture. Are these glueless clusters flukes, or do they point to a deeper truth about dark matter's behavior in extreme environments? With new sky surveys mapping millions of clusters in unprecedented detail, we may soon find out whether the missing halos are a quirk or a clue that dark matter is far stranger than we ever imagined. The universe has a memory, and dark matter halos might be etching their histories into the faint afterglow of the Big Bang itself. When these invisible giants collide, simulations suggest they don't just pass through each other silently. They create ripples in spacetime so profound the shockwaves could linger for billions of years. Astronomers call these phantom imprints gravitational echoes, and they're hunting for them in the most unlikely of places: the cosmic microwave background, the oldest light in the universe. If found, these whispers from the cosmic dark could rewrite our understanding of how structure forms across the ages. The theory hinges on a bizarre property of dark matter halos: their sheer gravitational might. During a merger, two halos don't collide like billiard balls but slide through one another like ghosts, their overlapping gravitational fields creating violent distortions in the fabric of space. These distortions don't just vanish once the halos separate, they propagate outward at the speed of light, compressing and stretching spacetime like sound waves through air. Over epochs, these waves would cool and fade, but their signature subtle temperature variations in the cosmic microwave background might remain, etched like fingerprints on the universe's oldest photograph. One team at the Planck satellite mission claims to have spotted hints of these echoes. Analyzing patches of the microwave sky, they identified odd, crescent-shaped temperature fluctuations that align eerily with known galaxy cluster mergers. The patterns don't match predictions from standard cosmology, but they do fit models where colliding halos send shockwaves through the primordial plasma. It's as if we're seeing the afterglow of dark matter's ancient battles, preserved in the universe's first light. Skeptics argue these signals could be statistical noise or artifacts from interstellar dust. But supporters point to a smoking gun. The echoes appear preferentially around massive galaxy clusters, precisely where halo mergers should be most frequent. Even more compelling, some echoes seem to point back to void regions where halos should have merged long ago but left no visible trace. If confirmed, this would mean the cosmic microwave background isn't just a relic of the Big Bang, but a palimpsest recording every major dark matter collision in cosmic history. The implications are staggering. Successfully mapping these echoes could let us reconstruct the merger history of the universe, revealing which halos collided when and with what force. It would be like archaeologists uncovering an invisible timeline of cosmic evolution, written not in stone but in spacetime itself. Future observatories like the CMB S4 project aim to scan the microwave sky with unprecedented precision, hunting for these whispers in the static. If they find them, we might finally crack dark matter's greatest secret, not by seeing it directly, but by reading the scars it left on the dawn of time. Imagine finding a galaxy where the stars are so few and far between, you could cross its entire length and barely glimpse a handful of suns. Now imagine that same galaxy, nearly invisible to telescopes, weighs as much as our Milky Way. This isn't hypothetical, it's Dragonfly 44, a cosmic paradox floating in the Coma cluster where dark matter doesn't just dominate the scene, it hijacks it entirely. Less than 0.01% of this galaxy's mass comes from stars and gas, the rest is an invisible behemoth. A dark matter halo so massive it defies every expectation of how galaxies should form. What makes Dragonfly 44 and its kin so baffling isn't just their darkness, but their defiance of logic. In the standard playbook of galaxy formation, dark matter halos act as gravitational wells, pulling in gas that eventually ignites into stars. The more massive the halo, the brighter the galaxy should be. Yet here we have a halo that followed the first step, growing to Milky Way proportions, but somehow skipped the second, leaving behind a ghostly skeleton of a galaxy. It's like building a mansion and furnishing it with a single light bulb. One theory suggests these ghost galaxies might be cosmic failures. Early in their history, perhaps a surge of ultraviolet radiation from neighboring galaxies, sterilized their gas reserves before stars could form in earnest. Imagine a fledgling galaxy, its dark matter halo ready and waiting, only for the gas needed to birth stars to be ripped away by cosmic winds. The halo remains a silent monument to what might have been. But there's a wilder possibility. These halos might be prisons. Some models propose that in dense galaxy clusters, tidal forces could strip away a galaxy's stars over billions of years while leaving the dark matter halo intact. Picture a tree losing its leaves one by one until only the invisible roots remain. If true, Dragonfly 44 might not be a failed galaxy at all, but the survivor of a prolonged cosmic robbery, its stars and gas stolen by larger neighbors, its dark matter skeleton left standing. The most unsettling implication, these ghosts might be everywhere. Surveys of galaxy clusters reveal dozens of ultra-diffuse galaxies with similar dark matter dominance, and some astronomers suspect they're just the tip of the iceberg. If halos can exist without galaxies, or with galaxies so faint we've barely detected them, our cosmic maps could be missing an entire population of dark matter structures, invisible cities dotting the universe, unseen and unaccounted for. Dragonfly 44 forces us to confront an uncomfortable truth. Dark matter halos don't need galaxies to exist. They might be the universe's default architecture, with stars and gas as mere optional decorations. If that's the case, our understanding of cosmic structure isn't just incomplete, it might be backwards. Instead of galaxies building themselves within halos, halos could be the true scaffolding of the universe, with galaxies as fleeting ornaments, here today and gone tomorrow. The ghosts are trying to tell us something. The question is, are we listening? Quantum physics and cosmology have long operated in separate realms, one governing the impossibly small, the other the unimaginably vast. But what if dark matter halos are where these worlds collide? Beneath their cosmic scale mysteries, these invisible structures might harbor quantum behaviors that defy classical physics, creating ripple effects across the universe. It's a radical idea that the same bizarre rules governing atoms could shape the largest structures in existence. Consider the puzzle of halo cores. Simulations predict dark matter should pile up densely at galaxy centers, forming sharp peaks. Yet observations reveal gentle plateaus, as if some force prevents overpacking. Quantum mechanics offers a tantalizing explanation: the Pauli exclusion principle. Just as electrons avoid occupying the same state in an atom, dark matter particles might resist crowding beyond a critical density. Picture trying to stuff too many marbles into a jar, except the marbles themselves refuse to be squeezed too tightly, not by physical barriers but by fundamental laws of probability. Then there's the enigma of wave-like dark matter. Some theorists propose that dark matter could exist as ultra-light particles, their wavelengths stretching parsecs across. Instead of discrete particles, halos would behave like colossal quantum clouds, vibrating with interference patterns that sculpt their density. This fuzzy, dark matter could explain why small halos are rarer than predicted. Quantum jitter might smooth out the smallest gravitational wells before they can form. It's as if the universe has a minimum resolution, blurring dark matter structures below a certain scale. The wildest possibility: quantum entanglement across cosmic distances. If dark matter particles became entangled in the early universe, their spooky connections might influence how halos align or interact today. Imagine two halos separated by billions of light years, their dark matter still communicating instantaneously through quantum links. While this defies classical intuition, it could offer a mechanism for the eerie large-scale alignments astronomers observe. Critics argue quantum effects should wash out at halo scales, but nature keeps surprising us. Recent studies of superfluid dark matter suggest quantum coherence might persist even in megastructures, with halos acting like Bose-Einstein condensates on galactic scales. In this model, dark matter wouldn't just clump, it would flow, creating vortices and density waves reminiscent of liquid helium's quantum turbulence. The implications are staggering. If quantum phenomena shape halos, we're not just missing a piece of the cosmic puzzle, we're missing an entire dimension of physics. Telescopes can't see these effects directly, but subtle fingerprints might lurk in galactic rotation curves or lensing anomalies. Future experiments like quantum gravity sensors could hunt for faint signatures, bridging the gap between the cosmos and the quantum realm. One thing's clear: if dark matter halos obey quantum rules, the universe is far stranger and more interconnected than we ever dreamed. Gravity may bend light, but dark matter halos twist it into signatures as unique as fingerprints, distortions so precise they could reveal the invisible architecture of the cosmos. When light from distant galaxies travels past these massive structures, it doesn't just curve slightly. It fractures into surreal arcs, rings, and even multiple images of the same object, like a funhouse mirror crafted by the universe itself. But here's the breakthrough: not all halos warp light the same way. Some create crisp, symmetrical lenses, while others produce jagged, uneven distortions. And these differences might be the key to unlocking dark matter's best-kept secrets. Take the case of the Einstein cross, a rare configuration where a single quasar appears quadrupled around a foreground galaxy. This perfect symmetry suggests a halo with an exceptionally smooth, evenly distributed mass, a cosmic rarity. Contrast that with MAX J0142, a galaxy cluster whose lensed images look like shattered glass, fragmented into chaotic streaks, the culprit. A halo so clumpy and asymmetrical, its gravitational field resembles a stormy sea rather than a placid pond. These aren't just aesthetic differences, they're direct traces of how dark matter is arranged inside the halo, hinting at whether it's cold, warm, or something even stranger. The magic lies in the details. Cold dark matter, the leading theory, predicts halos should be densely packed with countless tiny subhalos, like lumps in a cosmic gravy. These minuscule clumps would subtly perturb lensed images, creating telltale kinks or bright spots within the arcs. Warm dark matter, on the other hand, would suppress these small-scale structures, resulting in smoother, more pristine lenses. Recent observations of the galaxy cluster Able 3827 revealed something astonishing. A lensed galaxy stretched into a zigzag pattern, as if something invisible had taken a bite out of it. Some researchers argue this could be the smoking gun of a subhalo collision, direct evidence of dark matter's granularity. But the plot thickens. Certain halos produce lenses that defy both cold and warm dark matter models entirely. The Dragonfly arc in cluster SDSS J1148+1930 shows filaments of light so bizarrely contorted. They imply a halo with swirling internal currents, almost as if dark matter inside isn't just sitting there, but churning like a viscous fluid. Could this mean dark matter experiences friction or pressure, or that it interacts with itself in ways we've never imagined? The answer might lie in a new generation of telescopes, like the upcoming Euclid mission, which will map millions of lenses with unprecedented precision. What's truly revolutionary is how these fingerprints could settle decades-old debates. If certain lensing patterns correlate with galaxy type, merger history, or cosmic environment, we might finally crack the code of how halos evolve over time. Already, anomalies like the dark core in cluster Able 520, where lenses indicate a gravity well with no visible matter at all, are pushing us toward radical ideas that halos might have distinct flavors or evolutionary stages, each leaving its own mark on the light passing through. Every warped image, every fractured quasar is a message from the dark side of the universe. And as we learn to read these gravitational hieroglyphs, we're not just mapping halos, we're decoding the very language of the unseen. Stretching across the cosmos in a vast, intricate tapestry, the cosmic web connects every galaxy and cluster through ethereal threads of dark matter, a structure so immense it makes individual halos look like mere beads strung along its filaments. Far from isolated islands, dark matter halos are the bustling intersections of this grand design, where gravity's pull orchestrates the flow of galaxies and gas like celestial traffic converging at invisible hubs. Picture the universe as a spider's web after a rainstorm, droplets clinging to every silken strand, except here, the droplets are galaxies, and the web itself is woven from the unseen fabric of dark matter. The magic happens where filaments intersect. Here, dark matter halos grow fat on a steady diet of gas and smaller galaxies funneled along these highways. Simulations reveal halos acting like cosmic sponges, soaking up matter from multiple filaments at once, their gravity pulling in resources from all directions. The result, galaxy clusters, the universe's most massive structures, often sit at these junctions, fed by streams of material flowing along dark matter's hidden rails. The Coma cluster, for instance, anchors a node where at least 3 major filaments converge, its halo gorged on the bounty of this gravitational infrastructure. But the web's influence doesn't stop at feeding halos, it shapes their very evolution. Galaxies born along filaments spiral toward halos in predictable paths, like leaves caught in a river's current. Astronomers have spotted this choreography in action. The Pisces-Perseus supercluster shows galaxies lining up along filaments like pearls on a string, all streaming toward the supercluster's central halo. This orderly procession defies randomness, suggesting dark matter's threads don't just connect the cosmos, they direct it, yet some filaments behave oddly. The dark flow phenomenon reveals entire clusters drifting toward unseen attractors beyond the observable universe, as if the web extends farther than we can see, its filaments tugging halos like marionette strings. Even stranger are filament galaxies, objects like NGC 2664, which orbit perpendicular to their local filament, spinning like tops on a tightrope. Such anomalies hint that dark matter's cosmic web isn't a static scaffold but a dynamic, almost living structure, thrumming with forces we've yet to name. Perhaps the web's greatest marvel is how it bridges scales. The same filaments that feed galaxy clusters also guide lone dwarf galaxies, weaving them into halos with delicate precision. In the local group, the Milky Way and Andromeda are linked by a faint filamentary bridge, their future collision preordained by this dark matter causeway. It's a reminder that no halo, no matter how isolated it seems, is ever truly alone. The cosmic web doesn't just structure the universe, it animates it. Every filament is a conveyor belt, every halo a nexus, and together they form the universe's circulatory system, pumping galaxies and gas toward destinations set in motion billions of years ago. To understand dark matter halos is to trace their place in this grand architecture, where invisible threads write the story of everything we see and everything we don't. Every dark matter halo tells a story, not in words, but in the hidden contours of its structure and the silent rhythms of its motion. Scientists are now uncovering something astonishing. These invisible giants might carry imprints of their birth, preserving memories of cosmic events billions of years old. It's as if each halo encodes its own autobiography in the way its particles are arranged, how fast they spin, even the subtle asymmetries in its shape. The implications are staggering. If halos truly remember their past, we could be staring at a cosmic history book written in invisible ink. Take the case of the Milky Way's own halo. Recent studies of its outer regions reveal a surprising lumpiness, clumps and streams of stars moving in unexpected patterns, like guests at a party who refuse to mingle. These aren't random quirks, they're forensic evidence of ancient collisions, mergers, and near misses preserved in dark matter's gravitational embrace. Simulations suggest our halo might still bear scars from its most violent encounter, a head-on collision with another galaxy dubbed the Kraken, an event so cataclysmic it should have torn both galaxies apart. Yet here we are with a halo that somehow held itself together and remembers. Then there's the curious case of ghost halos, structures found orbiting larger galaxies that show no visible stars, just pure dark matter. Some, like the one trailing the galaxy NGC 3003, move in bizarrely elongated orbits as if they were slingshotted during an ancient cosmic battle. Astronomers suspect these could be the remnants of smaller halos that were shredded by tidal forces long ago, their stars stripped away while their dark matter cores survived, frozen in trajectories that replay their traumatic past. It's cosmic archaeology where gravity's fingerprints never fade. The most tantalizing clues come from halo spins. While most halos rotate sluggishly, a handful, like those hosting the galaxies NGC 2664 and UGC 1251, spin at nearly a third the speed of their galactic disks. This isn't random, it's a signature of how gas flowed into the halo during its infancy. Halos fed by smooth, coherent streams of matter tend to develop faster rotation, while those formed in chaotic environments spin more erratically or not at all. Like tree rings recording climate history, a halo's spin might encode the conditions of the early universe when it first took shape. Yet skeptics argue these memories could be illusions. Over billions of years, mergers and interactions should scramble a halo's original structure beyond recognition, like a snow globe shaken too many times. Some simulations show that even dramatic events like a close encounter with another massive halo leave surprisingly faint traces after just a few orbital cycles. If true, the patterns we see today might not be primordial imprints, but temporary wrinkles in an ever-changing dark matter landscape. The debate boils down to a profound question. Are halos cosmic elephants never forgetting, or cosmic goldfish resetting with each new interaction? The answer could redefine how we study galaxy formation. If halos remember, we might decode the universe's violent youth by studying their present-day structures. If they forget, we're left with only the faintest echoes of history, whispers drowned out by the noise of cosmic evolution. One thing's certain, dark matter halos aren't just passive containers for galaxies. They're dynamic entities with stories carved into their very fabric, waiting for us to learn how to read them. And with each new observation, we're peeling back another page in the universe's invisible memoir. Deep in the heart of dark matter halos, particles unlike anything in our standard model might be at work, shadowy entities with names like actions, sterile neutrinos, and WIMP. These aren't just hypothetical placeholders, they're leading candidates for what could actually compose the invisible bulk of the universe, and their existence would rewrite physics as we know it. The strangest part, each one would sculpt halos in totally unique ways, leaving gravitational fingerprints we're only now learning to trace. Take actions, theoretical particles so lightweight, trillions could pass through your hand every second without a trace. Unlike traditional dark matter candidates, actions wouldn't just sit idly in halos. They'd behave more like a cosmic superfluid, flowing and vibrating in quantum waves. This could explain why some halos have unusually smooth cores, as if their dark matter was stirred into a uniform haze. There's even a wild possibility that action halos could form Bose-Einstein condensates, exotic states of matter where particles act as a single quantum entity. Picture a galaxy's halo not as a cloud of discrete particles, but as a single, rippling quantum field stretching across light years. Then there are sterile neutrinos, ghostly cousins to the neutrinos we've detected, but far heavier and even more aloof. If these particles dominate halos, they'd leave a stark signature. Halos that are warmer and puffier than cold dark matter predicts, with fewer tiny subhalos. This might finally solve the missing satellites problem, where simulations overpredict the number of dwarf galaxies around the Milky Way. Recent observations of unexplained X-ray emissions near galaxy clusters could be the smoking gun, sterile neutrinos decaying into ordinary particles and releasing energy in the process. It's like catching dark matter mid-transformation, leaving a faint glow in its wake. But the plot twists further with WIMP, weakly interacting massive particles, long the favored dark matter candidate. These hefty particles would clump aggressively, creating halos dense with substructure. The catch, our most sensitive detectors, buried deep underground to shield from cosmic noise, have yet to confirm their existence. Some theorize WIMP might interact even more weakly than predicted, or that they're hiding in parameter spaces we haven't probed. Others wonder if dark matter isn't one thing, but a mix, actions in some halos, sterile neutrinos in others, like a cosmic particle buffet. The most tantalizing clues come from halo shapes. Action-rich halos might exhibit quantum interference patterns, creating faint ripples in their density. Sterile neutrino halos could appear more bloated, their edges less defined. And if dark matter interacts with itself through unknown forces, halos might show asymmetric distortions like cosmic clay molded by invisible hands. Already, anomalies in gravitational lensing, some halos bending light more sharply than expected, hint that we're not dealing with a single, simple particle. What's at stake isn't just the identity of dark matter, but the fundamental nature of reality. If actions exist, they could link halos to quantum physics on galactic scales. If sterile neutrinos are real, they might bridge the visible and invisible universe through rare, high-energy decays. And if WIMP finally show themselves, they could unveil a whole new sector of particle physics hiding in plain sight. The halos we can't see might be the very thing that forces us to rewrite the rules of the scene. Every unexplained rotation curve, every oddly smooth core, every missing satellite is a breadcrumb leading us deeper into the dark. And with experiments like the Action Dark Matter experiment and the upcoming Vera Rubin Observatory poised to hunt these particles in earnest, we might soon crack open the universe's best-kept secret. Until then, the halos remain silent, massive, and teeming with possibilities we've only begun to imagine. Staring into the far future of the universe, past the deaths of stars and the fading of galaxies, one question looms large: what becomes of dark matter halos? These invisible giants, which have shaped cosmic structure for billions of years, won't simply vanish when the lights go out. Their fate is tied to the universe's ultimate evolution, a slow-motion drama playing out over timescales so vast they dwarf human comprehension. Will they dissipate like smoke, collapse into unfathomable relics, or transform into something entirely new? The answers could rewrite not just cosmology, but the very laws of physics. Consider the simplest scenario: evaporation. In a universe dominated by dark energy, expanding at an ever-accelerating pace, even the mightiest halos might one day be torn apart. As space stretches, galaxies beyond our local group will eventually disappear beyond an unreachable horizon. The same expansion could weaken the gravitational bonds holding halos together, stretching them thinner until they dissolve into the void. Picture a sandcastle on a beach, slowly eroded by an incoming tide, except the tide is space-time itself, and the castle is a structure light years across. Some models suggest this process could take 100 trillion years or more, but in the end, even dark matter might not be immune to the universe's relentless expansion. But there's a twist: dark matter's fate might hinge on its still unknown properties. If it's made of particles that can decay, like hypothetical sterile neutrinos, halos could fade away long before expansion claims them. Over eons, these particles might break down into lighter, even more elusive entities, their mass converting to energy in faint bursts of radiation. Imagine a halo not as a permanent structure, but as a slow fuse burning imperceptibly, its particles winking out one by one across millennia. Yet if dark matter is truly stable, as most theories assume, halos could outlast every star, every planet, even every black hole, becoming the last structures standing in a cold, dark cosmos. Then there's the possibility of collapse. In a hypothetical Big Crunch scenario where the universe stops expanding and contracts back into a singularity, halos would face a far more violent end. Gravity would squeeze them into denser and denser configurations, their particles packed so tightly they might reach quantum limits we can't yet describe. Some speculate that under such extreme pressure, dark matter could undergo phase transitions like water, freezing into ice, forming exotic states of matter with bizarre properties. A collapsing halo might crystallize, fracture, or even ignite new physics as the universe runs in reverse toward its fiery birth. But the most mind-bending idea: transformation. If dark matter interacts with itself in ways we've yet to discover, halos might not just fade or collapse, they could evolve. In a paper published in 2022, physicist Lisa Randall proposed that dark matter might have its own dark forces, triggering phase changes over cosmic timescales. Halos could condense into dense spheres, unravel into filaments, or even coalesce into unseen dark matter stars, structures made entirely of the invisible stuff, burning with an energy we'd never detect. It's a reminder that the universe's final chapters might be written in a language we're only beginning to decipher. The irony is profound. Dark matter halos, which have guided the formation of everything we see, might outlast it all, silent witnesses to the universe's slow fade. Or they might unravel in ways that reveal their deepest secrets only in the cosmos's dying breaths. Whether they evaporate, collapse, or transform, their fate is more than a curiosity. It's a window into the ultimate nature of reality. And though we'll never see that future, the clues we uncover today might just let us glimpse the universe's last, invisible act. From ghostly halos that outweigh galaxies to invisible filaments stitching the cosmos together, These 25 mysteries have shattered our understanding of dark matter's hidden kingdoms. We've navigated halos that spin too slowly, vanish without a trace, heat up inexplicably, and even sprout quantum hairs, each discovery peeling back another layer of the universe's greatest enigma. These aren't just cosmic oddities, they're clues that dark matter might be far more dynamic, more bizarre than we ever imagined. It's as if we've spent decades studying an elephant by touch alone, only to realize we've been grasping at tendrils of some colossal, multidimensional creature. Consider how these puzzles redefine our place in the cosmos. The Milky Way isn't just a glittering spiral, it's a speck afloat in a million light-year-wide halo of invisible mass, its stars dancing to gravity's hidden tune. Galaxies aren't isolated islands but intersections in a dark matter web, their fates entwined by filaments we can't see. Even the Big Bang's afterglow might carry echoes of halo collisions from epochs beyond memory. Every mystery we've explored reveals how little we truly grasp about the universe's scaffolding and how much more thrilling the journey ahead will be. But here's the real magic. These aren't dead-end riddles. Each anomaly, the missing satellites, the cuspy cores, the too big to fail halos, is a breadcrumb leading toward a deeper truth. Maybe dark matter particles interact via unknown forces. Maybe they're entangled across cosmic distances, or perhaps, as the tidal streams and lensing distortions suggest, we're witnessing the shadow of an entirely new physics. The halos aren't just hiding their secrets, they're daring us to look closer. Now it's your turn. Which of these 25 mysteries set your mind ablaze? The ghost galaxies devoid of stars, the halos that remember their violent pasts, or the quantum quirks that might ripple through these cosmic giants. Drop your thoughts in the comments. Let's unravel these enigmas together. And if you're hungry for more deep space discoveries, hit subscribe. The universe has countless more secrets to spill, and we're just getting started.